You know, usually when we sit down for these deep dives, we're looking at a specific slice of the world. We're analyzing a new health trend or a shift in the stock market or maybe a new piece of legislation.
Yeah.
It's usually contained.
Yeah.
It has edges.
Right. It's a specific domain. You can kind of draw a circle around it.
But today feels different. We aren't just looking at a slice of the world. We are looking at the lens we use to view the world. We're looking at intelligence itself.
And not just our intelligence.
No, the audacious, I would say arguably arrogant attempt to build it from scratch. We are doing the foundations and history of artificial intelligence.
It is a massive topic. I mean, we're diving into the introduction of artificial intelligence, a modern approach, which is, for all intents and purposes, the Bible of the field.
The textbook.
It really is. And what strikes you immediately isn't the code or the algorithms, it's the philosophy, it's the history. The authors make this incredible point right off the bat. This isn't a story that started with silicon chips or Google.
Not at all.
This is a story that started when we first named ourselves.
Homo sapiens.
And the whys.
It really puts a stake in the ground, doesn't it? Of all the things we could have highlighted about our species, our ability to walk upright, our opposable thumbs, our use of tools, we chose our minds.
We defined our entire existence by our intelligence.
And that definition, it creates a paradox that has bothered philosophers for thousands of years. We define ourselves by this ability to think, to perceive, to predict. And yet we have almost no idea how we actually do it.
Exactly. The source material puts it so beautifully. How does a mere handful of matter, this wet biological tissue in our skulls, manage to perceive, understand, and manipulate a universe that is infinitely more complex than it is?
And that's really the core of our deep dive today. We aren't just asking how does the brain work? I mean, that's neuroscience.
A noble pursuit, but different.
It is. We're asking how can we build something else that works that way? Or maybe even works better.
That is the crucial distinction. It's the difference between a biologist studying a bird's wing and an engineer trying to build a plane. AI is the engineering side of the mystery of thought. It attempts to build intelligent entities.
There's a quote in the reading that I think just captures the excitement of this field perfectly. It compares AI to physics.
I love this part.
It says, you know, if you go into physics today, you have to accept that the absolute giants, Galileo, Newton, Einstein, they've already laid the pavement. The foundations are pretty much set.
You're refining the edges in physics. You aren't likely to, discover a whole new law of motion in your garage.
Right. But the text says that in AI, the field is so young that there are still openings for several full-time Einsteins and Edisons.
It's the Wild West. I mean, think about it. The term artificial intelligence wasn't even coined until 1956. In the grand scheme of science, that is literally yesterday.
We're still laying the bricks for the foundation.
We really are.
So, here's our mission for this deep dive. We're going to try to wrap our heads around this beast. First, we need to figure out what AI actually is, because as we'll see, even the experts fight about the definition.
Constantly.
Then we're going to trace the ingredients, the philosophy, the math, the psychology, all the different streams of thought that had to combine to make this possible.
And then we get to the history.
And the history is a roller coaster. It is not a straight line of progress.
Not at all. It's a cycle of incredible hype, massive failure, these so-called AI winters where funding just completely evaporated.
And then these sudden explosive renaissances, like the one we are absolutely living through right now.
For sure. But before we get to the history, we have to tackle that definition problem.
Right. I think if you stopped someone on the street today and asked, what is AI? They'd probably point to something like ChatGPT.
Or a self-driving car.
Or maybe a movie villain like the Terminator.
And, none of them would be wrong, but none of them would be totally right either. The authors of our source material suggest that we're all a bit confused because we're actually conflating different goals. They propose a grid. Imagine a square divided into 4 boxes.
Okay, let's visualize this. What are the axes of this grid?
The top axis is the focus. Are we interested in thought processes and reasoning? So do we care what's happening inside the brain of the machine?
Okay, the internal mechanics.
Or are we interested in behavior, just the output? What the machine actually does in the world. We don't care how it gets there.
Internal thought versus external action. Got it. What's the side axis?
The side axis is the standard of success. Are we trying to measure up to human performance? Do we want it to be like us, warts and all?
With all our biases and mistakes?
Potentially, yes. Or are we measuring it against ideal performance? Do we want it to be purely rational? to be perfect.
That's a really crucial distinction. Because humans are, well, we aren't always rational. We get tired, we get emotional, we make logical fallacies.
Exactly. So if you're building an AI to think humanly, you might actually want it to make certain human-like mistakes. If you're building it to act rationally, you want it to be better, be optimal.
Okay, let's walk through these 4 boxes because I think this really helps clarify the different tribes of AI researchers. Let's start with the one everyone knows, the top left corner, acting humanly.
This is the classic approach. This is the Turing test.
Alan Turing, 1950.
He basically said, look, defining intelligence or thinking is too hard, it's too philosophical, let's just make it operational.
The imitation game.
The imitation game. If you are typing back and forth with some entity, and after 5 minutes you cannot reliably tell if it is a person or a machine.
Then for all practical purposes, the machine is intelligent.
He argued, yes, it has passed the test.
But the source mentions that the Turing test isn't just about a chatbot. There's something called the total Turing test.
Yes, and this is where it gets incredibly, incredibly difficult. The standard test is just text. The total Turing test requires the machine to have a video feed and a little match to pass physical objects back and forth.
Whoa. So to pass that, you don't just need a good language model.
No. You need computer vision to see and interpret the video. You need robotics to manipulate the objects. You need knowledge representation to understand what the objects are. You need automated reasoning. You need machine learning.
You need the full stack of AI capabilities just to fool one human in one room.
You need everything.
So here's what surprised me in the reading, though. You would think that passing the Turing test is the ultimate goal, the holy grail of AI. But the text says that modern researchers, they don't really care about it.
It's true. For the most part, it's seen as a bit of a distraction now.
Why? I mean, it seems like the gold standard.
The authors use this fantastic analogy, and it has to do with aerodynamics. For centuries, humans wanted to fly. And because the only things we saw that could fly were birds and insects, we obsessed over mimicking them. We built wings that flapped. We tried to copy the structure of feathers.
The ornithopters of Leonardo da Vinci.
And they were all complete disasters. They never worked. The breakthrough for the Wright brothers wasn't that they mimicked a bird better. It was that they stopped the mimicry and started to understand the underlying principles of lift, drag, and thrust. They studied aerodynamics.
And I love that. We don't judge a Boeing 747 by how well it fools a pigeon into thinking it's a giant metal pigeon.
Exactly. Does this machine fly so exactly like a pigeon that it fools other pigeons? Is a terrible, useless test for an airplane. We want flight, not bird mimicry. In the same way, modern AI researchers want intelligence, not human mimicry.
We want the aerodynamics of thought.
That's the perfect way to put it, not just tricking someone into thinking they're talking to Bob from accounting.
Which brings us to the second box in the grid, thinking humanly. This is the field of cognitive modeling.
This is different from the Turing test. Because here, we do care about what's happening on the inside. We don't just want the computer to get the right answer. We want it to use the same cognitive steps that a human brain uses.
So if I solve a long division problem by, carrying the 1 and visualizing the numbers, this approach wants the computer to carry the 1 too, even if there's a faster, more direct computery way to do it.
Precisely. This is where AI and cognitive science really overlap. You saw this with Neil and Simon's general problem solver back in 1961. They weren't satisfied with the program just solving logic puzzles.
Right.
They interviewed human subjects, recorded them thinking out loud as they solved the same puzzles, and then they tried to get the program's internal trace of steps to match the human protocol.
That seems almost intentionally limiting. If we're trying to build something potentially smarter than us, why shackle it to our own messy, inefficient mental processes?
Well, it is limiting if your goal is pure engineering,
Mm-hmm.
but it's hugely valuable if your goal is science. If you can build a computer model that accurately predicts and explains human errors and reaction times, you can learn a tremendous amount about how the human brain actually works.
Okay, so it's a tool for psychology, but maybe not the best path to a super intelligent machine.
Probably not.
So let's move over to the ideal side of the grid, the rational side, where we leave biology behind.
This is where we look at logic and math. The third approach is thinking rationally. This goes all the way back to Aristotle. The laws of thought.
The syllogisms.
Socrates is a man. All men are mortal. Therefore, Socrates is mortal. The idea was that logic is like a perfect, clean language for thought. If you can just translate the real world into these logical symbols, you can use mathematical deduction to prove the correct answer to any question.
This was the dream of the logicist tradition, wasn't it? Just feed the world into the computer as a series of facts, press a button, and let it deduce the truth.
That was the dream, but it hit a massive wall. Two walls, actually.
What was the first one?
The first one is that the world isn't neat and tidy. It's messy. How do you write a formal, logical proof for something like, that joke was kind of funny, or it might rain later today? Informal, uncertain, common sense knowledge is incredibly hard to turn into, if A is true, then B must be true.
You can't capture nuance in a syllogism. And the second wall.
Computational exhaustion. We call it the difference between solving a problem in principle and solving it in practice. You might have a logical formula that guarantees you'll find the best chess move. But if it takes the computer 1,000,000,000,000 years to calculate it for a single move, the formula is useless.
Which leads us to the final box, and this is the one the text says is basically the winner, acting rationally.
The rational agent. This is, without a doubt, the dominant approach in modern AI research.
So define rational for us here, because usually when I hear that word, I think of someone really cold and calculating, like Mr. Spock.
In AI, the definition is much simpler and more powerful. An agent is just something that perceives and acts. A rational agent is something that acts to achieve the best outcome, or, in a world full of uncertainty, the best expected outcome.
And the key difference here is that it focuses entirely on the result, the action, not the thought process that got it there.
Right. The text uses the perfect example of a reflex. Imagine you touch a hot stove. You jerk your hand back.
Instantly, without thinking.
Exactly. Now, did you perform a logical syllogism in your head? Did you think, premise A, the stove is hot? Premise B, extreme heat damages human tissue? Conclusion, I must retract my hand.
No, of course not. I just moved.
But was the action rational?
Absolutely. It was the best possible action to take. It saved my hand from being burned.
And that's the point. Acting rationally includes logic. Sometimes carefully thinking through a problem is the best way to act, but it also allows for reflexes, for simple learned rules, for intuition. It's a much broader, more flexible, and more powerful definition.
So it's just about doing the right thing.
It's about doing the right thing. We define the goal, maximize the score in a game, clean the floor efficiently, drive to the destination safely, and the agent's job is to find the best policy to achieve that goal.
So we have our target, the rational agent. That's what we're trying to build. But as we said at the top, this idea didn't just appear out of thin air in 1956. The foundations section of this text is like a who's who of intellectual history.
It's humbling, really. You realize that AI isn't one field. It's the convergence point of about 8 different massive disciplines. You've got philosophy, mathematics, economics, neuroscience, psychology.
The list goes on.
It does. Computer engineering, control theory, linguistics.
Let's peel these back a bit, because some of them are obvious, like, of course, you need math and computer engineering, but some, like philosophy, you might not expect to be so technical.
Philosophy is the absolute bedrock. We already mentioned Aristotle, but he didn't just give us the rules for logic. He actually wrote down what looks for all the world like pseudocode for an AI planning algorithm.
You're kidding. In 400 BC.
I'm serious. He wrote about means-ends analysis. He laid it out. I need a cloak. To have a cloak, I need to make one. To make one, I need the material. To get the material. He was breaking a complex, high-level goal down into a sequence of smaller executable steps. That is exactly how a modern robot plans a task.
Wow. And philosophy also gave us the fundamental debate that makes AI even conceivable in the first place, the mind-body problem.
Right. You have Rene Descartes on one side. He was a dualist. He looked at the human body and said, okay, the blood and the bones, it's just mechanics, it's machine. It follows the laws of physics. But the mind, the soul, that is something else entirely. It's non-physical. It sits outside of nature.
And if Descartes was right, AI is impossible. You can't write code for a non-physical soul.
You can't. If the mind isn't part of the physical world, you can't build one out of silicon or anything else. So AI as a field relies entirely on the alternative view. Materialism.
The idea that the brain is just a machine.
A very complex, wet, biological machine, for sure. But a machine nonetheless. The brain's operations constitute the mind. And if the mind is just physics operating on matter, then in principle, we can replicate it.
That leads us pretty smoothly into mathematics, because once you accept that the mind is a machine, you need a language to describe and program that machine.
And for centuries, that language was logic. George Boole in the 1800s gave us Boolean logic. True or false, on or off, 1 or 0. That is the native tongue of every digital computer ever built.
But math didn't just give us the tools, it also gave us the warnings. It gave us the stop signs.
Big ones. This is Kurt Gödel.
Gödel's incompleteness theorem.
It's a bit of a mind bender, but he essentially proved that in any formal logical system powerful enough to describe arithmetic, there will always be statements that are true, but that cannot be proved within the system.
Meaning, logic itself has holes. There are limits to what it can prove.
There are fundamental limits to proof. And then Alan Turing and Alonzo Church came along and showed there are limits to computation itself, the idea of computability. They proved that there are some functions that no computer, no matter how powerful, can ever calculate.
So we know from the start that we can't solve everything, but there's a much more practical problem than impossible. There's intractable.
Yes, and this is the theory of NP completeness. This is absolutely vital for understanding why early AI failed and why modern AI succeeds. An intractable problem is one where, as you add just a little bit more complexity, the time it takes to solve it explodes exponentially.
Can you give us an example?
The classic one is the traveling salesperson problem. You have to visit 10 cities and you want to find the shortest possible route.
Yeah.
Hard, but a computer can calculate it by checking the options.
Okay.
Now add just one more city, so you have 11. It doesn't get 10% harder. It gets 11 times harder. By the time you have 50 or 60 cities, checking every possible route would take longer than the age of the universe, even on the fastest supercomputer.
And the real world has a lot more than 60 cities to consider for any given problem.
The text has a great line. The world is an extremely large problem instance. So math taught AI a hard lesson early on. You cannot just brute force your way to intelligence. You need cleverness. You need shortcuts. You need heuristics. You need probability.
Which brings us to another ingredient I wouldn't have expected. Economics.
I know, it sounds weird, right?
Right.
Why would economics be a foundation for AI?
Yeah, I assume we aren't talking about inflation and federal interest rates.
No. We are talking about decision theory. Think about Adam Smith. He treated the economy as a collection of individual agents, each one trying to maximize their own well-being.
They are acting rationally.
They are acting rationally. Economics is the science of making decisions under uncertainty to get what you want. And that gave AI two huge tools, utility theory and game theory.
Utility theory is just a way of putting a number on how much I want something, right?
Mathematically, yes. If I like pizza more than I like salad, I assign a higher utility number to the pizza. It allows a computer to weigh options in a concrete way. I could turn left, which has a 90% chance of a good outcome, utility 5, or turn right, which has a 20% chance of a great outcome, utility 20. It turns complex choices into math.
And game theory.
That's what you need when you aren't alone.
Right.
If I'm a robot and I'm just moving rocks around a warehouse, I only need utility theory. But if I'm a robot playing chess against you, now I need game theory. My best move depends on your best move.
I have to model what you're thinking.
You have to model your opponent. This is absolutely crucial for things like self-driving cars. They have to constantly run game theoretic models of what the other human drivers on the road are likely to do.
This is getting incredibly complex. We have the philosophy of mind, the math of logic and probability, the economics of decision-making. But we still need the actual hardware. We need to look at neuroscience.
And the comparison the text makes between biological brains and digital computers is startling, and it's not what you'd expect.
Well, computers are faster, right? That's the common wisdom.
Whoa, way, way faster. On a component level,
Yeah.
a modern transistor can switch states in about a nanosecond, a billionth of a second. A neuron in your brain, it's sluggish. It takes a millisecond, a thousandth of a second to fire.
So the computer's basic parts are literally 1,000,000 times faster.
1,000,000 times faster. So the immediate question is, why aren't computers 1,000,000 times smarter than us? Or at least, why weren't they from the very beginning?
It must be the architecture, the wiring.
It's the architecture. The brain makes up for that slowness with sheer massive parallelism. You have roughly 100 billion neurons, and each of those is connected to thousands of other neurons. You have something on the order of 100 trillion synapses.
So while the computer is doing one super fast thing at a time,
The brain is doing billions and billions of slow things all at once. And that structure, that massive web of simple interconnected units, is the direct inspiration for artificial neural networks.
and this all leads to a really empowering conclusion for AI researchers.
Yes, the text says it clearly. A collection of simple cells can lead to thought, action, and consciousness. Or, even more simply, brains cause minds.
There's no magic smoke.
There's no magic smoke. It's just wiring. And if it's just wiring, we can, in theory, solder it.
But before we could solder it, we had to understand behavior. And this is where psychology comes in. And it was a bit of a tug of war.
A massive conflict, really. In the first half of the 20th century, psychology was completely dominated by behaviorism. People like John B. Watson and B.F. Skinner.
The rats in a box and pigeons playing ping pong guys.
Exactly. And their whole philosophy was, do not talk about what's happening inside the head. Mental processes, introspection, consciousness, that's unscientific. It's just folk psychology. The only things you can measure scientifically are the stimulus, what you do to the animal, and the response, what the animal does back.
They treated the mind as a black box.
A complete black box. And that's incredibly unhelpful if your job is to build what's inside the box.
You can't engineer a mind if you're not even allowed to talk about things like memory or goals or planning.
It was incredibly stifling for the nascent field of AI. Fortunately, in the mid-20th century, we got the cognitive revolution.
The rise of cognitive psychology.
Right. And a key figure here was Kenneth Craig. In 1943, he really nailed this. He viewed the brain not as a black box that just produces reflexes, but as an information processing device. He said that any rational agent must carry a small-scale model of reality in its head.
So it's not just reacting, it's actively simulating the world.
It's simulating possible futures to decide on the best present action. Craig even specified the 3 key steps of a knowledge-based agent. First, the stimulus must be translated into an internal representation. Second, this representation is manipulated through reasoning. And third, the results are retranslated back into action.
That is basically the blueprint for every intelligent agent system built since.
It really is.
We also have to give credit to the engineers. We've talked about all these abstract ideas, but someone had to actually build the machines.
Absolutely. Computer engineering. You can't have artificial intelligence without the artifact. And this goes back further than you might think, long before the silicon chip. We have to talk about Ada Lovelace.
The first programmer in the 1840s.
Working on Charles Babbage's theoretical analytical engine. Now, Babbage just saw it as a massive mechanical calculator. But Lovelace saw something much, much deeper. She realized that if the machine could manipulate numbers, and if numbers could be used to represent other things like musical notes or logical symbols, then the machine wasn't just a calculator.
It can manipulate ideas.
It could manipulate abstract concepts. She famously speculated that the engine might one day compose elaborate and scientific pieces of music of any degree of complexity or extent.
She predicted AI-generated music in 1843. That's staggering.
It's an unbelievable leap of imagination for someone working by candlelight with gears and levers.
Fast forward 100 years, and the intense pressure of World War II gives us the first real electronic computers.
The Colossus, built by Turing's team at Bletchley Park, and the ENIAC in the United States. These were room-sized monsters built with vacuum tubes, but they proved that large-scale, electronic, programmable computation was possible.
Okay, just a couple more ingredients before we can finally get to the birth of AI. We need control theory and linguistics.
Control theory is vital, and it's another one with ancient roots. It's the study of self-regulating systems. The modern version is Norbert Wiener's work on cybernetics from the late 1940s.
What's the core idea there?
It's all about the feedback loop, about minimizing error. Think of a simple thermostat. It has a goal state, 70 degrees. It measures the current state, 68 degrees. It calculates the error, -2 degrees. It then takes an action turning on the heat to reduce that error.
That seems so simple, but that loop, goal, measure, act, that's how a robot learns to walk, isn't it?
It's how a robot stays upright. It's how a self-driving car stays in its lane. It is a constant, high-speed process of error correction.
And finally, linguistics.
This brings us back to our old friend B.F. Skinner, the behaviorist. He wrote a book called Verbal Behavior, where he tried to claim that language was just another learned habit. You learn to say the word cookie because you get rewarded with a cookie.
And a young linguist named Noam Chomsky just completely destroyed that idea.
He obliterated it in a famous review. He pointed out that children say sentences they have literally never heard before. They combine words in novel ways. That means language can't just be imitation. Children must have some kind of internal program, a grammar, that allows them to generate creative language.
And this gave birth to computational linguistics.
The effort to understand language not as a set of habits, but as a formal system that could be analyzed and potentially computed.
So the table is set. It's the mid-1950s. The ingredients are all there. We have materialist philosophy, formal logic, probability theory, the economics of rationality, the blueprint of the neuron, the blueprint of the cognitive agent, and the actual computers to run it all on.
And that brings us to part 3 of our outline, the history of AI. And as we said, hold on tight. because this is not a smooth linear ride.
It starts with what the text calls the gestation period, 1943 to 1955.
This is the pre-dawn. You have Warren McCulloch and Walter Pitts, who in 1943 published a paper proposing the first mathematical model of an artificial neuron. They showed that if you connect these simple on-off switches together in the right networks, you can compute any logical function.
That's the theoretical birth of the neural network.
It is. And then a few years later, you have two guys, Marvin Minsky and Dean Edmonds, who actually went and built one in 1950, the SNARC.
And this is my favorite detail in the whole text. What did they build it out of?
They built it out of 3,000 vacuum tubes and the surplus autopilot mechanism from a B-24 bomber.
That is just incredible. They literally used leftover parts from World War II to build a rudimentary brain.
It simulated 40 neurons. It was basically a simulated rat that could learn its way through a maze. And it worked. But the official capital B birth of AI as a field happens in 1956.
The Dartmouth Workshop.
This is the Woodstock of AI. John McCarthy, Marvin Minsky, Claude Shannon, Nathaniel Rochester. They organized this 2-month-long workshop, bringing together 10 top researchers.
And the proposal they wrote to get funding for this workshop, it's famous for its incredible optimism, or maybe arrogance.
It's breathtaking. They wrote, "We propose that a 2-month, 10-man study of artificial intelligence be carried out. The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it."
We can basically solve the brain in a summer with 10 smart guys.
That was the vibe.
Yeah.
They thought if they just got in a room and really focused, they could make a significant, maybe even decisive breakthrough.
And did they?
Well, they didn't solve AI. Not even close. But they did debut something that blew everyone away. Newell and Simon brought a program they'd written called the Logic Theorist.
What did it do?
It was a reasoning program. It was designed to prove mathematical theorems from the famous book Principia Mathematica.
And it wasn't just copying proofs that humans had already done. It was actually finding new ones.
That's the amazing part. For one of the theorems, it found a proof that was actually shorter and more elegant than the one the original human authors, Russell and Whitehead, had found.
That must have been a shock. A machine doing creative mathematical work.
It was a massive validation of their whole premise. And it kicked off the first great era of the field, early enthusiasm, from about 1952 to 1969.
John McCarthy called this the look ma no hands era.
They were just knocking down barriers left and right. Arthur Samuel wrote a checkers program that could learn to play by playing against itself.
And this was huge because of the machine learning aspect.
Hugely significant. Because until then, the common criticism was that computers could only do what they were explicitly told to do. Samuel's program disproved that. You could tell a computer how to learn, and it could eventually become better than its creator. Samuel was a mediocre checkers player, but his program became a master.
During this time, we also saw the birth of Lisp.
John McCarthy invented Lisp in 1958. It became the dominant programming language for AI research for the next 30 years. It was designed from the ground up to process symbols and lists, not just numbers.
And they started to solve problems in these things called micro-worlds.
This was the main strategy.
Yeah.
The real world is just too big and messy, so let's create a tiny, simple, perfect world and solve problems there. The most famous was the blocks world.
Just a simulated table with some colored blocks on it.
Exactly. And a program called SHRDLU could understand natural language commands about this world. You could pick up the big red block or put the green block on the blue block.
They would do it.
It would do it. And it could even understand complex instructions like find a block which is taller than the one you were holding and put it into the box. And it would reason through the steps and do it. It looked like they'd cracked it. Language, reasoning, planning, learning. It was all happening.
The optimism must have been off the charts.
Completely. Herbert Simon in 1957 predicted that a computer would be the world chess champion within 10 years.
He was off by about 40 years.
Just a bit. And that runaway optimism led directly to the first crash. The period the text calls a dose of reality, 1966 to 1973.
So what went wrong? What was the reality check?
3 big things. First, the spirit is willing problem, which is to say machine translation.
Ah, the famous story. Tell it.
So during the Cold War, the U.S. government was pouring money into automatically translating Russian documents. They thought it would be simple. Just create a big electronic dictionary and swap the Russian word for the equivalent English word.
A simple lookup table.
A lookup table. But of course, language doesn't work that way. The apocryphal story is that they fed the system the biblical phrase, the spirit is willing, but the flesh is weak. The computer translated into Russian and then back into English to check its work. And what came out was, the vodka is good, but the meat is rotten.
That is hilarious, but it shows exactly what was missing. Context, understanding.
It shows that without background knowledge about the world, knowing what a spirit implies in a religious context, what flesh means metaphorically, word-for-word translation is a disaster. The government realized they were burning money, a report came out, and all the funding was canceled.
Okay, so that's problem one. What was the second?
The math came back to bite them. Intractability, the combinatorial explosion.
Yeah.
Those programs that worked so beautifully on 4 blocks in the micro world completely fell apart when you gave them 40 blocks. The number of possibilities grew exponentially, and the computers just ground to a halt. They couldn't scale up to real-world problems.
And the third problem was actually a book called Perceptrons.
By Marvin Minsky and Seymour Papert. They did a very rigorous mathematical analysis of the simple, single-layer neural networks of the day, the perceptrons. And they proved that these simple networks were fundamentally incapable of solving certain basic logical problems, like the XOR function.
And instead of taking this as a challenge to build more complex, multi-layer networks,
The community took it as a death sentence for the entire approach. It was a wet blanket thrown over the whole field of connectionism. Funding for neural networks dried up almost completely for over a decade. This is the first AI winter.
but like any winter, it eventually ended. And the field regrouped, moving into the era of knowledge-based systems from about 1969 to 1979.
The researchers realized something important. The early AI, like the general problem solver, tried to be smart about everything, which meant it ended up being very shallow. It didn't know much about any specific thing.
So they flipped the script.
They flipped it completely. They said, let's stop trying to create a general intelligence. Let's make an AI that knows a lot about one very narrow thing. The expert system. The classic example is Dandrol. It was a system designed to infer the molecular structure of organic compounds from mass spectrometry data.
That sounds incredibly niche.
It is, and that's precisely why it worked. Instead of trying to reason from the first principles of quantum physics, the creators interviewed expert human chemists. They codified the rules of thumb and heuristics that chemists use. If you see a peak at this particular mass, it's probably this kind of molecular fragment. They packed the system with this specific, hard-won human knowledge.
And there was another big one, MyCIM.
MyCIN was designed to diagnose blood infections. It had about 450 rules derived from extensive interviews with doctors. And in trials, it actually performed better than junior doctors at the Stanford Medical School.
And it introduced a key concept for dealing with the real world, right?
Yes, certainty factors. Because medicine isn't black and white. A doctor doesn't say you 100% have meningitis. They say, based on these symptoms, there's a strong probability, maybe 80%, that it's meningitis. MyCIN could handle that kind of uncertainty.
This success must have woken up the corporate world. This is where AI becomes an industry.
It is. 1980 to the present, really. The first massive commercial success was a system called R1, built for Digital Equipment Corporation, or DEC. It helped configure the complex orders for their new VX computers.
And how much did that one system save them?
The estimates were it was saving the company about $40 million a year.
Wow. Okay, that's a number that gets a CEO's attention.
Gets everyone's attention. Suddenly, every Fortune 500 company wanted an expert systems division. There was a massive boom. Billions of dollars poured in. The Japanese government launched its 5th-generation project, aiming to dominate the future of computing.
But we know how the story goes. Boom is often followed by bust.
And it was. The second AI winter hit in the late 80s.
What killed the expert systems this time?
They were just too brittle. They were expensive to build and maintain. You had to manually interview experts and code thousands of rules. And if the world changed slightly, or if you asked a question that was just a little outside its narrow domain, the whole system would break. It couldn't learn or adapt.
The knowledge was canned, not grown.
Exactly. The hype outran the reality. Companies failed to deliver on extravagant promises, and the bubble burst.
But while the corporate world was panicking and defunding projects, the scientists were quietly going back and fixing the old problems. The return of neural networks.
Mid-1980s, a few different research groups working in parallel reinvented a crucial algorithm called backpropagation.
And this is the fix for the problem Minsky and Papert pointed out in their book, right?
It's the fix. It was a way to efficiently train neural networks that had multiple layers. We could finally solve those complex problems like XOR that had stumped the early simple models. This new field was called connectionism, and it brought the brain-like approach roaring back into the game.
And at the same time, the rest of AI started to grow up. The text says it adopted the scientific method.
This was a huge cultural shift in the late 80s. Before then, a lot of AI research was, frankly, just building a cool demo and writing a paper about it. Look at this neat thing I built.
Not very rigorous.
Not at all. The field started to demand rigor. It became, here is my theorem, here's my data, and here is my reproducible experiment that you can verify.
Speech recognition is the perfect example of this shift.
It is. In the 70s, they tried to build speech recognition systems by writing down explicit rules about phonetics and grammar. It was a messy failure. In the 80s, they switched to a new approach, hidden Markov models, or HMMs.
What's an HMM?
It's a rigorous mathematical framework based on probability theory. They stopped trying to teach the computer linguistics and just started training it on vast amounts of data. They'd say, here's a sound wave, and here's the text that corresponds to it. You figure out the statistical patterns.
And that fundamental shift from trying to teach rules to letting the machine learn from data, that really sets the stage for the entire modern era, doesn't it? Part 4, the data revolution.
This is the world we are living in now, and it started with a really profound realization around the year 2001. Often, having more data is better than having a smarter algorithm.
There was a famous paper by Banco and Brill from Microsoft Research that really proved this.
They were looking at a complex language, problem word sense disambiguation. They took 4 different learning algorithms, from a pretty mediocre one to the state-of-the-art one at the time, and they fed them progressively more and more training data.
And what happened?
The mediocre algorithm with 1 billion words of data absolutely crushed the best, smartest algorithm that only had 1 million words. The lesson was clear.
Quantity has a quality all its own.
Precisely. We realized we had been stuck in a knowledge bottleneck. We were trying to hand-code all the knowledge of the world into our machines, but the world is just too big. The solution was to stop trying to spoon-feed the machine and just let it read the entire internet.
There's another incredible example with photos. The Hayes and Efros experiment from 2007.
Oh, the scene completion problem. This is great. Say you have a beautiful photo of a landscape, but there's an ugly telephone pole right in the middle. You want to digitally remove it and have the AI fill in the hole?
Photoshop magic.
Right. But how does it know what to fill it with? If you have a database of, say, 10,000 photos, the AI tries to find a patch of sky or grass from another photo to stick in the hole, but it usually looks wrong. The lighting doesn't match, the texture is off.
Okay.
But Hayes and Efros didn't use 10,000 photos. They used a database of 2 million photos.
And what was the result?
It was perfect. It was seamless. Because with 2 million photos, you are almost guaranteed to find another photo taken at the same time of day with the same kind of lighting that has the exact patch of sky or grass you need. The computer didn't need to be smart about art. It just needed a massive memory of the world.
This brings us right up to the present day. So let's talk about the state of the art. What can this data-driven AI actually do now?
The source material lists some incredible concrete achievements that were already happening 15, 20 years ago.
Let's start with driving.
Robotic vehicles. In 2005, a robot car from Stanford named Stanley won the DARPA Grand Challenge. It drove itself with no human control for 132 miles across the Mojave Desert.
And that was just the desert. Then came the Urban Challenge.
BAS, from Carnegie Mellon. It successfully drove in a simulated city environment, obeying traffic laws, dealing with other cars, merging, parking. This was in 2007.
What about planning? This is an area people don't often see, but it's huge.
It's one of the biggest, most impactful, and unseen victories for AI, the DART system. During the first Persian Gulf crisis in 1991, the U.S. military had to plan the movement of 50,000 vehicles, personnel, and cargo to the theater of operations. It was a logistical nightmare.
And they used an AI to plan it.
They used the DART planning tool. And here is the kicker. A later report from DARPA stated that this single application saved so much time and money that it paid back all of the funding DARPA had invested in AI research over the previous 30 years.
That is a staggering statistic. Every failed robot, every vodka is rotten translation mistake, all of it was paid for by one successful logistics program.
That's the power of the rational agent approach. When it works, the efficiency gains can be absolutely astronomical.
And, of course, we can't talk about the state of the art without talking about games.
Deep Blue, 1997. IBM's purpose-built chess machine plays Garry Kasparov, the reigning world chess champion, the greatest player in history. It wins the 6-game match, 3.5 to 2.5. And Kasparov was genuinely shaken. He said he felt a new kind of intelligence across the board from him. IDM stock value rose by $18 billion.
And maybe the quiet, unsung hero of modern AI, spam fighting.
We take it so for granted now, but do you remember what email was like in the early 2000s? It was becoming unusable.
Oh, yeah. I was a torrent of junk.
Now, Bayesian learning algorithms, rational agents, classify billions upon billions of messages a day, quietly filtering out 99.9% of that junk. They save humanity countless hours of wasted time. It's a rational agent acting on your behalf to keep your inbox clean.
And machine translation, the original failure, has finally been redeemed.
Completely. We now have statistical models of language built from training on trillions of words of text. The text mentions a startling fact. We now have state-of-the-art Arabic to English translation systems built by scientists at Google who don't speak a word of Arabic. The math and the data do the translation, not the human linguist.
So we've come a long, long way. We've gone from Aristotle syllogisms to vacuum tube neurons through the boom and bust of the AI winters to these massive data-driven rational agents that are quietly running huge parts of our world today.
We move from trying to imitate the biology of the bird to trying to understand the fundamental aerodynamics of intelligence. And we realize that being rational, acting in a way that best achieves your goals, is the most powerful and general way to engineer intelligence.
But the source material leaves us with one final provocative thought, a little bit of humility to end on.
It addresses the idea of the singularity, this futurist concept that computers will just keep getting smarter and smarter until they rapidly leave us in the dust. But the authors bring us back to those hardware numbers we talked about earlier.
The raw complexity of the brain versus the computer.
Right. And they make this point. Even if you could build a computer with infinite capacity, unlimited storage, unlimited processing speed, that's just the hardware. We still don't know what the program is.
We don't know the software that the mind is running.
We don't. We know that brains cause minds, but we still don't know how. We have no idea how that storm of electrochemical signals in our neurons becomes the subjective experience of seeing the color red or the smell of coffee or the feeling of nostalgia or the understanding of a sarcastic joke.
We're getting better and better at building the computer, but we're still searching for the ghost in the machine, or at least for its source code.
It's the ultimate scientific mystery. And as the text said right at the beginning, there's still plenty of openings for a few full-time Einsteins.
Well, on that note, thanks for listening to this deep dive into the foundations of AI. It's a story that is very much still being written, and we're all living in the middle of the next chapter.
Stay curious.